So this session is on linear layers. There will be 3 talks. And the first talk will be Decomposing Linear Layers by Christophe Behaile, Patrick Felke, Gregor Leander, and Sondre Ronjam. And Gregor will give the talk.
Thank you very much. Is this working? Yes, maybe. Yeah, okay. Yes, so I'm going to talk about designs that don't follow the best practice, maybe. So there are certainly open designs, cryptographic designs, which where you have a public specification, where you have design rationales and security arguments. But there are also closed designs where, for one reason or the other, not all of this is fulfilled. So maybe we don't have a public specification, maybe we do not have design rationales, or maybe we don't have security analysis. Yeah, and examples for the later case is things that was not supposed to be public and only got reverse engineered, like the GA1 ciphers. Then Simon and Speck is a famous example, where we have a public specification, but we do not have any design rationales. And this tree-block that we already heard this morning, where we don't have any design rationale, and actually it's even a bit more hidden what was done. So there are different levels of closed design here. Okay, so this tree-block, just to recall, it's a Russian standard, a hash function. And I'm going to give a bit more details because this is like a running example throughout the talk. So this operates on the 64-bit state, where we have an 8-bit S box, which was just given as a lookup table, where you have a permutation of bytes, and the 64 by 64 binary matrix that is applied in 8 times in parallel. So this is the specification of the cipher. And we don't have any design arguments how those things were chosen. And so given such a design, a natural research question is, how do we recover structure? Now, how do we understand where is this design coming from? And for the S boxes, this is well studied. So there are very nice results how the S box was chosen. I don't know, but at least the structure that's in there is by now well understood to a large extent, I would say. And for the linear layer, it's not so well studied. So we don't have good tools to find structure in linear layers, and this is what our work is about. So we focus on the linear layer, and the idea is, given a binary matrix, every linear layer can be represented as a binary matrix, recover structure, and especially so there could be all kinds of structure. We focus on something very particular, so we certainly do not solve this problem entirely, but we focus on the question of, can we find structure that is induced by constructions over extended fields, so like the AES mixed color. So, and if we further structure this in 3 problems, the first one is exactly this: given a binary matrix, how can we decide if this actually is better represented as a matrix over an extension field? The second part is an obfuscated version of the first one, and I'm going to explain what I mean by obfuscated version later. And then the third one is like a follow-up question. If you then know that this is actually a matrix over an extension field, what kind of matrix is this? Does it follow some well-known construction, for example, for MDS matrices? Okay, and in this talk, I'm mainly talking about this first problem. And then for the second and third one, I'm briefly motivating and giving the results, but no details, no technical details. Okay, so the field structure. Just to be more clear what I want to do, I'm given a matrix, in this example, a 12 by 12 matrix. And I want to know if this matrix could be represented as a matrix over the extended field of 2 to the 4 elements. So that's the question. So can I write this as a 3 by 3 matrix, where each of these blocks, let's try to use this one so you can see in Zoom, where each of these blocks actually corresponds to multiplication with a finite field element, so out of the form gamma to some power, where gamma is a generator in this finite field. Okay, so this is the question we want to solve in this first part of the talk. So usually we represent a finite field by picking an irreducible polynomial and thinking about multiplication of polynomials modulo this irreducible polynomial. That's certainly the most general and not the most common way of doing so, but there's much more general ways of representing a finite field as a matrix by matrices, finite field elements by matrices. And I'll briefly motivate why in this area of SPN ciphers we might actually observe things that are more general than just polynomials. So if we consider 2 round SPNs, or 1.5 or whatever, yeah, so S-box layer, linear layer, S-box layer, what you can always do, think of in changing the specification, either because it was just reverse engineered or because you want to hide something, is you can certainly put small linear layers after the S-boxes and the inverse right after, so that you actually did not change anything. And you can do the same after the linear layer. No? So we didn't do any changes to the functionality. And then to make it nice for the round before and after, you're going to put T and T inverse before and after. And now we end up with a design which is functionally equivalent to what we started with, but which has a different S-box, which I don't care in this talk, but which also has a different linear layer. Yeah, and if I started with a linear layer over the finite field, so if L was actually defined over the finite field, you can think of what happened in terms of matrices is that this matrix, this binary matrix L, was now multiplied from left and right with block diagonal matrices corresponding where on the blocks you have this T and T inverse. And so coming back to the matrix representations of an extension field, if I start with a field which is represented as you know, by choosing an irreducible polynomial, what I end up now is that each of these elements will be left and right multiplied with T and T inverse. Yeah? And they still form a finite field. So I don't give a formal proof here, but yeah, it's just conjugating these field elements. You still have the same properties. And just one example, so if you have 2 field elements and you modify them this way and you multiply, you get field elements. And this means that we have to do something a bit more clever than exhaustively searching, because even for small sizes, the number of T and T inverses is large. So now the problem becomes, given a set of matrices, binary matrices, can we decide if they correspond to field multiplication or not? Okay. And then this set S is normally would just be the blocks of our matrix that we started with. Okay. So we start easy, we just take one element. So how can I decide if one given matrix of size S times S, so a matrix A, which has to be invertible, but because otherwise it's certainly not a field multiplication, so I'm only going to consider invertible matrices. Is this a field multiplication or not? Can I represent this as a field multiplication or not? That's equivalent to the minimal polynomial of the matrix A being irreducible. Okay, that is basically how all these irreducible polynomials come into play. Yeah. I'm not going to give a proof here. Let's focus on the next more complicated case. Now I don't have 2, not only one matrix, but many matrices, all these blocks, and I still want to know the same question, is this a field, can I represent this as a field or not? So what I have to do now is not only check something about irreducible polynomials, but we also have to check if if they fit together, these matrices. That's the main point. And so what we have, the statement that we prove in the paper, I'll give a short proof here, is that this is a finite field, is a representation of a finite field, if and only if the multiplicative subgroup is cyclic and the generator of this subgroup has a primitive, has an irreducible minimal polynomial. Okay, and just let me give you a short proof. So if it's cyclic and generated by an irreducible minimal polynomial, that's exactly the lemma before. So this direction is clear, and also the other direction is not a lot more complicated. If you have a field, then the multiplicative group is cyclic, and then you take a generator, and this is going to generate this matrix is going to generate this subring, and by the previous lemma, this minimal polynomial of alpha has to be irreducible. Okay, so this is not too hard to see. And now the question is how to make this into an algorithmic approach. Yeah? So how can we algorithmically verify this thing? And the main problem is maybe algorithmically checking if the minimal polynomial, computing the minimal polynomial is easy, and checking for irreducibility is easy. So what is not as straightforward maybe is how to check if it's cyclic or not. Okay. So how do we check if a group given by n generators is a cyclic group or not? Okay. And so there's one lemma which is very nice. If I'm reducing again complexity by looking at two cases first. So if I have a group which is generated by two elements, and I know this group is cyclic, then I can easily find the generator by taking a suitable product of those two elements. So I can always, even without knowing that G is cyclic, I can always write down this this element, but then it's not a generator. But if it's a cyclic group, then I'm going to get a generator of the cyclic group in such a way. And now this is just for two elements, but you can just apply this lemma recursively to kick out, to reduce the number of generators in your group one by one. Okay. So this is the algorithm that does exactly this. So first, you're given these n matrices, and you want to know if the multiplicative group is cyclic and if this corresponds to a finite, if the polynomial is irreducible. So you first use this algorithm to find something which generates the group if it's cyclic. So we still have to check if this really is a generator or not. So this is why we call it a pseudo generator. So this we can easily compute, and then we're going to check if all these other matrices, if all these AIs are elements in this subring by using the additive structure, using linear algebra to check if we can represent them, if they are in the span of these things. So if they are a linear combination of these powers of alpha, and if not, then we know it's not the field. And if yes, then we know it's alpha is indeed the generator. And then we test if it's a real reducible polynomial. And then if not, we say it's not a field. And otherwise we found that it's a field, and we actually computed a generator. Okay. And the nice thing is that up to factorizing 2 to the s minus 1, this is a polynomial time, so that's very fast. And for the s which we are interested in, so s is basically the size of the block size, not the block size, but the s box size. So that's will always, in all interesting practical cases, be easy to factorize. So application to Stribok, it's a second, or a fraction of a second, and you'll get the field representation. So this was actually known before. So there was like handcrafted algorithm to check, and so it actually it's just running through irreducible polynomials. You would not find that it's a field structure directly, but you had to transpose. Okay, now basically this is more automatic, and no handcraft needed. Okay, so there's hidden structure in the linear layer of Stribok. Okay. So then second part was obfuscation and more structure. And as I said, I will be very brief on this. So looking back on the choice that we had, so now it's either the choice that that happens because we are just reverse engineering things, and so maybe we do not get the intended representation, or because we really want to hide structure. If you want to really hide structure, you can of course put much more different things. So there's no reason why all the T and T inverses have to be the same in the first round, and there's no reason not to put different ones after the linear layer, and then you get something which is much more hidden. So this also is not the field representation. So even if L is defined over the finite field, this is not anymore. And in the paper we explain how to recover this field representation efficiently, up to things that you cannot. So there's no unique representation anymore, but it's again feasible to do efficiently. And then finally, what more can be said after, for example, we found in this tree boxing that there is a finite field hidden, if you want. What more can be said? So then we also give ways to test if some heavily obfuscated, so like of the form I just showed on the slide before, if this actually corresponds to a Cauchy MDS matrix. And again, because of this heavy obfuscation, it's technically a bit involved, and the details can be found in the paper. And if you then apply this to this Russian standard, you did see that not only was it hidden that there's a field structure, but also it's actually a known construction for MDS matrices, namely this Cauchy construction. And I think that's all I wanted to say. Thank you very much.
Thank you, Gregor. So we have time for questions. Are there any questions in Beijing? Yes, no question. Do you have questions in Kobe? Okay, I have one question, maybe two. So you identify this hidden structure in the Stribog matrix.
Yeah.
So I guess for me, the obvious question: do you see any possible problem with this structure? Did you try to think about this? Potentially some interplay with the S-box as well, with the I don't know much about the S-box in Stribog, but maybe there's some interplay with this structure as well.
Yes, maybe there's some. So we did not think too much about it. My personal feeling, it's unlikely, but yeah, we certainly cannot exclude it.
Maybe a joint work with Leo in the future.
We are looking into this, but it's not.
Okay, thank you very much.
You have a question?
Oh, we have a question. Okay.
Oh.
So not really a question, but just on this possible interaction between the S-box and the linear layer. The S-box is defined in the same field. So the S-box, it's nice, thanks, by the way, representation is in the same field as the linear layer. But I agree that at this point, beyond this, I cannot say anything. Yeah. That's the official version, yes.
Yeah, so my opinion is it's not. I would be super impressed if they put a backdoor in this. No, but I would be super impressed, and my feeling is I don't think I'm so impressed. No.
So did you try same thing with Kuzniaczek matrix? I mean, that also is the same as box and.
But there's already a construction given, right?
No, I don't
think so.
think it's given. It's in a different field, yeah.
Yes, but there's,
Right.
I mean, it's not, I mean, there we know that is coming from there.
Okay. Thank you.
Okay, if no more question, let's thank Gregor again. Oh, okay. But the person.
Hi, this is Ainid Venkateshwarlu.
Okay, thank you. I will introduce your talk. Okay, so sorry. All right, so the next talk is on the lower bound of cost of NDS matrices by Ainid Venkateshwarlu, Abhishek Kesarwarni, and Sumanta Sarkar. And Ayenedi will give the talk online. Thank you. You have to share the screen. Okay, I think
Yeah.
he's doing it.
Hi all, this is Ayenedi Venkateshwarlu. I will be presenting our paper on the lower bound of cost of MDS matrices. This is a joint work with Abhishek Kesarwani and Sumanta Sarkar. As you can see from the title, this is about MDS matrices in the context of lightweight cryptography. In this work, we established the lower bound on the cost of 4x4 block MDS matrices under the metric called SWXR or sequential XR based on words. Here is the outline of my talk. I will briefly introduce basic concepts, and then we see some preliminary results in settling the lower bound. Finally, we discuss some limitations of our work and open questions. As you all know, MDS matrices are best suited for designing diffusion layers because they provide optimal diffusion. Matrices can be implemented using circuits with XR gates. And the main question here is finding MDS matrices with minimal hardware cost, that is requiring least number of XR gates for the parameters of practical interest. The general form of this problem can be stated like this: minimizing the number of XR gates necessary to compute a set of linear functions. This is also known as shortest linear program problem. It is known to be NP hard. For this reason, given a matrix, finding optimal implementation is hard. An m by m matrix over the field F2 to the power n is MDS if all its square submatrices are non-singular. In this work, we consider block matrices. Here is the notation that we use in our presentation. M and M denote the ring of m by m block MDS matrices with entries from n by n binary matrices. GLN is a general linear group of non-singular matrices. DNM is the block diagonal matrices where the entries are non-singular matrices. PNM is the block-wise permutation matrices. A block and MDS block matrix M in MNM is said to be MDS if all its square block submatrices are non-singular. There are mainly three metrics discussed in the literature to assess the cost of matrices. The first one is DXR or direct XR. It is the number of ones in a binary matrix minus size of the matrix. It gives a good upper bound on the cost of the matrix. Another one is SXR or the sequential XR. It is the number of bitwise XR operations in a sequential program with in-place operations. That an in-place operation is like this: given an input vector x1 to xn, replacing xi with xi plus xj. This can be viewed as a elementary row operation of type 3 on the input vector x1 to xn. That's why, given a matrix M, we consider decompositions of this form, where P is a permutation matrix, C's are elementary matrices of type 3. Each matrix corresponds to the operation xi replacing with xi plus xj. It costs 1 xr. So we want to minimize the number of type 3 matrices involved in the decomposition. The minimum such T gives the SXR. Here we do not use any extra registers to store the intermediate values. By allowing extra registers, one may get a better estimate. This is known as GXR. This is related to the SLP problem. And also it is hard. So for this reason, computing GXR for a given matrix is a hard problem. Similarly, SXR is related to optimal pivoting using Gaussian elimination. It is also a hard problem. So computing SXR of a given matrix is also a hard problem. The most popular choice for designing a diffusion layers is 4x4 block MDS matrices, where the entry is coming from GL and F2. The least cost of a known matrix in the case of n equal to 4 is 35, and it is 67 in the case of n equal to 8. The main question here is whether we can get better matrices. It is still an open problem. What we do in this work is we establish that this is the best that we can achieve if you consider the new metric SWXR. Now we present some preliminary results used in establishing the lower bound. As you know, elementary matrices are related to elementary row operations, and these are obtained by applying elementary row operations on the identity matrix. A block identity matrix of order M over GLNF2 is denoted by INM. This is nothing but identity matrix of order Mn over the binary field, and viewing it as in a block form. There are three types of elementary matrices corresponding to three types of elementary row operations. The first one corresponds to interchanging two rows of a matrix. The second one corresponds to multiplying a row by a non-zero scalar. The third one corresponds to adding a scalar multiple of a row to the another row. These are denoted by Eij, Eij of A, Eij of B, where AB in the case of block matrices, these are n by n matrices, and these are known as coefficients, and Ij are the indices. Here B can be singular, but we wanted matrix decompositions using type 3 matrices with non-singular coefficient matrices. As you all know from linear algebra, any non-singular matrix can be decomposed as a product of elementary matrices. Even in the case of block matrix, if it is non-singular, it can be written as a product of elementary block matrices of type 1, type 2, type 3, where type 2 and type 3 matrices, coefficient matrices are non-singular. As you all know, a matrix can have a variety of decompositions. Given a decomposition, one can reorder these elementary matrices by using these identities. Here you can observe that multiplying a type 2 or type 3 matrix by a type 1 matrix simply changes the coefficient, the indices of the type 2, type 3 matrices, but there is no change in coefficients. Similarly, multiplying a type 3 matrix with type 2, there is a change in the coefficient, but there is no change in the indices of the type 3 matrices. Using these identities, we can reorder the elementary matrices in a given decomposition. Using the first lemma, one can move all the type 1 matrices to the left or right by appropriately changing the coefficients of the appropriately changing the indices of the type 2 and type 3 matrices, so that we can get a decomposition of this form where P is a block permutation matrix corresponding to the all the type 1 elementary block matrices, and the remaining portion is product of only type 2 and type 3 matrices. Using the second lemma, we can move all the type 2 matrices to the left and get a decomposition of this form where P is a block permutation matrix, D is a block diagonal matrix, which is the product of type 2 matrices, by appropriately modifying the coefficient, but there is no change in the indices of the type 3 matrices. This is the portion of product of type 3 matrices. We can have these kind of decompositions, and given a decomposition, one can easily compute mx by applying g1 to gk iteratively on the input vector x. So the cost of implementing m is equal to the sum of the cost of the implementing g1 to gk. The SXR cost of type 1 matrix is 0 because it is simply a permutation. SXR cost of a type 2 matrix is equal to SXR of its coefficient matrix A. In the case of type 3 matrix, the SXR of type 3 matrix is equal to n if B is a permutation matrix. If it is not a permutation matrix, it is greater than or equal to n plus 1. Similar to the SXR, we consider decompositions of this form where P is a block permutation matrix. Since its cost is 0, we want to separate it and look at the other portion, which is a product of type 2 and type 3 matrices with non-singular coefficients. The SWXR of the block matrix M is minimum over all such decompositions of this form. We can also see that given a block matrix, and we get a variety of matrices which have the same SWXR cost. Here PIs are block permutation matrix, DIs are block diagonal matrix, whose entries are again permutation matrices over F2. And the inverse of M and M transpose also have the same SWXR cost. Not only that, these four matrices are also MDS if M is MDS, and also they preserve the cost, SWXR cost. Now we discuss the main ideas in settling the lower bound in our search technique. A path of length L is an ordered list of elementary block matrices of type 3, ignoring the coefficient matrices. So you can view it as an ordered list of tuples consisting of row and column indices of the type 3 matrices. The matrix generated by this path is having a decomposition of this form, where we have this type 3 form, and we take P and Q to be block permutation matrices, and D to be a block diagonal matrix. A matrix having this kind of decomposition is belong to this path, or this matrix can be generated by this path. Similarly, we can also consider this kind of paths, because a type 2 matrix, if you want to reorder type product of type 2 and type 3, it doesn't alter the indices of the type 3 matrices. Because we are only worried about the indices, we can also consider decompositions of this form. Either you consider this decomposition or this decomposition, a matrix having this decomposition, we say that it is belong to this path B. A matrix can have variety of decomposition, so a matrix can be generated by a variety of paths. We want to see what are all the paths that can generate the same set of matrices. Observe that in a product of two type 3 matrices, they commute with each other if the indices satisfy this relation. It has no dependency on the coefficients if it satisfies this relation. So in a path, if the indices satisfy this relation, you can reorder these elements, and then the reordered path also generate the same set of matrices. Not only that, if you have in a path, if two consecutive elements having the same indices, they can be clubbed together to a single element. So the path of length L can be reduced to a path of length L minus 1. That also generate the same set of matrices. Another way of getting new paths to which generate the same set of matrices is by applying a permutation on the indices of the given path. This is called a conjugate of the path, because we consider all possible permutations here. That actually makes we can incorporate this also. So this way, this path also generate the same set of matrices. So using these relations, we define what are known as equivalence classes of these paths. Suppose we have two paths of the same length, the path B is equivalent to path B prime if it is a conjugate of a path obtained by iteratively applying valid exchanges on the path B. What do you mean by valid exchange? If you two consecutive elements commute with each other, then you simply reorder those elements. Like that, you can apply sequence of these reorderings and then finally take a conjugation, you get the path. As you can see from the earlier discussion, these two paths generate the same set of matrices. If B is equivalent to B prime, then they both generate the same set of matrices. This way we can club several paths into an equivalence class, and now we club few more such equivalence classes to extend these equivalence classes. Given a path B and a matrix generated by this path B, M inverse can be given by this decomposition. M transpose has this decomposition, and you can see that these are related to this path. Simply reversing this order of this path, you can see that this M inverse is generated by this path, and simply exchanging the column and row indices of these entries, we get that inverse of the transpose matrix is generated by this path. So we club all these four into an extended equivalence class. The main result here is, if you take two paths in an extended equivalence class, and if one path can generate an MDS matrix, and you can also get an MDS matrix using the other path, because if M is MDS, all these matrices are also MDS. Not only that, they all have the same cost. So if you can generate a matrix, MDS matrix using one path having some cost, then you can also generate an MDS matrix with the other path having the same cost. So you can, if you want to search for low cost MDS matrices, it is enough to test for only one representative path of these equivalence classes, and this greatly reduces the search technique, search complexity. So we use this idea to search low cost matrices. From the Wong et al.'s paper, we know that the smallest path that can generate MDS matrices is of length 8. First, they actually searched for matrices over the finite field f2 to the power n, searching all the paths of length 8. There are 12 power 8 paths, and the best that they can get is having cost 8n plus 3. So this matches the known result. They could not improve the known matrices. Then they tried to search over GL4F2 or GLNF2. Their search complexity is huge, so they could not establish whether there exist matrices with cost less than or equal to 8n plus 2. What we do in this work is we present an algorithm to identify potential paths of length 8 that can generate MDS matrices. As discussed, it is enough to test only representative paths of the extended equivalence classes. So we see that finally there are only 2 such paths up to extended equivalence class that can generate MDS matrices. By applying some transformations, and we see that even these 2 paths we cannot generate 4 by 4 block matrices having cost 8n plus 2. There are 12 power 8 paths because there are 12 type 3 matrices, and we want to check for potential paths that can generate MDS matrices. First, we eliminate all those paths that can be shortened. That means only paths of length less than 8 cannot generate MDS matrices. So we eliminate all those paths. Then from the remaining paths, we consider only representative paths of these extended equivalence classes. Then we search only those representative set of paths symbolically, whether they can verify MDS matrices. You can check the paper for the details. We use symbolic computation, treating these elements as of a free algebra on the indeterminants of the coefficient matrices. Out of these 12 power 8 paths, only 2 non-equivalent paths remain which can generate MDS matrices. Now we take these 2 paths presented here, the representatives of those 2 equivalence classes, and we check whether these 2 paths can generate MDS matrices with cost less than or equal to 8n plus 2. We consider the first path, and a matrix generated by a first path is of this form like this, and the coefficient matrices are given by these A's and B's. If there exists a matrix with cost 8n plus 2, what we can have is only at most 2 of these coefficient matrices can be non-permutation. All others must be permutation matrices. Because there are 8 type 3 matrices, 8n is already fixed, and only you can have additional 2. So only 2 of these coefficient matrices can be non-permutation. All the remaining are permutation matrices. There are 36 matrices. There are 24 permutations. If you want to exhaustively search, it's a huge task. What we do is we just look at the elements of this form like this, which are sum of 2 monomials, and we look for all such elements in M and M inverse. Observe that if observe the expression in the bracketed portion, this is a sum of 2 monomials. If all these coefficient matrices are permutation matrices, then this sum becomes singular matrix. So because sum of 2 permutations is a singular matrix, if you want this to be non-singular matrix, then at least one of the coefficient matrix appearing here in this expression must be non-singular matrix. This way we identify which pair of elements can be non-singular matrices, non-permutation matrices, and we identify that only there exists only one pair of elements, that is B4 and B5 can be non-permutation, and all the remaining must be permutations if you want to have a matrix with 8n plus 2. We then further apply some transformations and then verify whether with such a choice whether we can get a MDS matrix. Even this fails in the case of testing 2 by 2 submatrices. So what we see is we check similarly the other paths. What we see is both these paths cannot generate MDS matrices whose cost is less than or equal to 8n plus 2. So what we see is that the minimum SWXR cost of 4 by 4 block MDS matrix must be at least 8n plus 3. By using extended equivalence classes and some transformations, we are able to establish the lower bound on the cost of 4 by 4 block MDS matrices under this metric SWXR cost metric. If you want to get better matrices, we have to use other metrics such as SXR or GXR. In this metric, in this search technique, we have not considered depth parameter. By including depth parameter, one can search for low cost matrices. And also, this is we only worked with 4 by 4 matrices. If you want, we can extend these ideas for higher order matrices, but the search complexity grows drastically. So we can probably use some heuristic techniques to search for low cost matrices in higher order matrices. That's all. Thank you for your attention.
Thank you, Ayenidi. So do we have questions in Beijing? We have maybe just time for one question.
There's a question in Beijing.
Okay.
Hello.
Hello.
In the previous work, Wang Shi et al. They proved some lower bound of not only the MDS matrices but also the evolutionary matrix. So I want to know if your method can be used in the evolutionary matrices.
Yeah, we can use this technique.
Okay, but in the previous, I tried to use the method in the evolutionary, but the effects maybe not good in the MDS matrices. So I think it can.
All that we have to do is we have to actually take permutations into consideration. We have to insert permutation in between so that we can make involutory matrices, because type 1 matrices changes the indices of the type 3 matrices. So we have to, this is actually, we are also looking into this kind of approach to find low cost involutory MDS matrices.
Yeah, okay. I think it may be the problem of the SWXR. Yeah, thank you. Thank you.
Yeah.
Okay, thank you. I think we don't have more time for other questions. So let's thank the speaker again. All right. So the last talk of the session will be more input makes difference. Implementation of linear layers using gates with more than 2 inputs. This is a paper written by Kun Liu, Weijia Wang, Ling Sun, Yang Hong Fan, Li Xuan Wu, and Meixing Wang. And the speaker will be Kung Liu in Beijing. You have to share the screen, if possible.
There any technical issue? Okay.
Yeah. Good afternoon, everyone. Okay, it's an honor for me to present our paper today, and it's a joint work with 王伟佳、孙玲、樊友红、吴丽轩, and Wang Miqin. I'll talk from the 6 aspects, and let's start by discussing some background information. And first, I have a question for you: how to apply ciphers in results-constrained devices? Yeah, that's why we are interested in the lightweight cryptography. In recent years, lightweight cryptography has become a major focus in the cryptography community due to the rapid development of the lightweight devices, such as the Internet of Things and radio frequency identification tags. And these devices have limited resources in terms of the circuit size, the power consumption, and the latency. Therefore, we have to expand the limitation to these devices. And generally speaking, the direction is divided. There are two directions. Now, first, we can design new lightweight primitive that can efficient in hardware and software efficient. And another method is to optimize the existing implementations that can aid in designing new primitives. And the criteria is about the power, energy, throughput, area, and latency. And in practice, the diffusion and confusion components are relevant to the linear and nonlinear operations. And in this paper, our work mainly focuses on the area of the linear layers, such as the mixed columns in AES. And then we talk about the motivation and contribution. And this is the AES run function, and the MC is the mixed columns. And if we can reduce the area of the mixed columns, we can significantly reduce the area of the AES run function. To illustrate this point, we show the example. The example, we have a trivial circuit. It requires 8 XORs. And if 1 XOR requires 2 GE, the circuit requires 16 GE. But after our optimization method, we can get a new circuit. It only have 4 XOR gates and half the number of the GE. So this example demonstrates that after optimization method, we can reduce the area of the cipher. There are many work to optimize the linear layers, but most of them focus on the 2-input XOR gates. As we all know, the standard libraries can support 3-input XORs or 4-input gates. So we can use multi-input gates to reduce the area further. And there are 2 methods to do this. One method is proposed by Bex et al. It search a circuit directly, but it increased the searching space because the large number of XOR types. And another method is proposed by Bendick et al. It uses a transform strategy to convert a circuit using 2 inputs into the circuit using 3 inputs XOR gates, but it may require more candidates to get a better circuit. And our paper follows this line of work and propose a transforming framework. It can transform a circuit using gates with no more than n inputs into the circuit using gates with no more than n+1 inputs. The framework requires a graphic extending algorithm. We can see the figure. First, we have a given circuit with m input XORs, and then we use a graphic extending algorithm to generate the 5 equivalent circuits, or maybe 500, 5,000. It's impossible. And then we use a framework to convert the circuits into many new circuits with m+1 input XORs. And then we can choose the best one with the lowest area as our results. And we apply the framework to many linear layers to block ciphers, such as AES, Two-Fish, and et al. With 2, 3, 4 inputs XOR gates. And this is our experiment. We test 500 and 5,500 matrices. The BP is using 2 inputs XOR gates, and the EJT2 and EJT3 is our algorithm using multi-input XOR gates. On average, the area of each matrix is reduced by 21%. And then we talk about some new aspects for XRP problem. The SLP problem is defined as finding a solution with a minimum number of x's to compute the multiplication of the matrix. And it has many applications such as the optimization, the computational geometry, and the operations research. But it is proven to be NP hard, so no efficient algorithm can solve it exactly. But there are many heuristics to find suboptimal solutions. But we have a new question. The SLP problem focuses on the minimum x's, but we focus on the lowest area. It's different. So we propose the SLPA problem. It's an SLP problem with the lowest area. We use the epsilon operation. It's an operation containing epsilon 2 inputs XOR gates. Then given the cost of every operation, the metric is defined as the following equation. Using the following equation, we can find the lower area of the circuit. And then we provide two definitions. And first is the DAG. A directed cyclic graph is a directed graph that has no cycles. And it's important that no cycle because if a graph has a cycle, it's wrong in hardware. We cannot implement in hardware. And another definition is the topological ordering. It can help us to control nodes in correct ordering. And then we talk about the graph extending algorithm. We can see the example, the node 0 to node 7 is the input nodes or the unit nodes. And the following equation represents the circuit requires 10 XOR gates. For example, the TA01 means the node is the sum of the node 0 and node 1, and the underline on node 12 is represent the node 12 is the output values or the target value. And we will use the example to show our technique. First, we introduce two definitions. The single graph is a directed graph so that each non-unit node has only one imputations. The single graph, like the equation 1, it is the imputation used in hardware to implement the linear layer. Another definition is the extended graph. In the extended graph, each node can have more than one imputation, like the equation 2. We can see the node 10 is the sum of node 4 and node 5, or the sum of node 14 and node 15. So it cannot be used in hardware, but we will use it to optimize our imputations. And this is the method to generate the extended graph, and the graph uses the definition of the reachability set on the right. In the table, for each node, there is at least one path from the node to its reachability set. And then next question is how to split the extended graph. Because the extended graph is wrong in hardware, we cannot use it. So we propose a simple method. We can choose every implementation of a node in extended graph. We can see the example in GS0, the node 7 is the sum of node 13 and node 14. And in GS31, the node 7 is the sum of node 9 and node 15. It's different. And use our method in our example, we can generate 32 single graphs based on the extended graph. And next, we need to do some further optimization. After splitting the extended graph, the nodes in different single graphs may have different degrees and out degrees. The out degree 0 means that the node is not used to generate other nodes. So maybe we can remove it, and we will give the property to check if a node is redundant. And we use the method in our example. In the 32 graphs, we found 12 graphs have one redundant node and 2 graphs have 2 redundant nodes, and we remove that. But when we check the final results, we found some graphs are wrong. The wrong graph is an correct circuit for the corresponding matrix, which usually contains the cycles in the graph. You can see the example on the right. In the figure, the node E, node F, and node G consist of a cycle. So it's wrong in hardware. We cannot use the figure to implement the linear layers in hardware. So we checked all the graphs in our example. We found only 16 graphs are wrong and 16 graphs are right. In the right graphs, we find 4 graphs has 9 XOR grids and we list them, we can choose anyone as our best results, and they can be optimized by our framework. And this is the algorithm. It have 4 steps. First, we need to generate the extended graph based on a single graph. That is the imitation of the linear layer. And then we need to split the extended graph into many equivalent circuits. And then we need to remove redundant nodes. And finally, we need to delete wrong graphs. And then these graphs can be optimized by our framework. And next, we'll introduce the transforming framework. Before we introduce the transforming framework, we need to do some limitation. For example, if we use G3 XOR matrix, only 2, 3, 4 inputs XOR gates can be used. This limitation can reduce the searching space. And then we can do the transformation from the equation on the left to the equation on the right. After transformation, the area of the circuit is reduced. And before we introduce the framework, we have 3 questions need to answer. The first question is, which node can be removed when we receive a implementation of the linear layers? And the question 2 is how to remove one node when we found the nodes can be removed. And the third question is, when we found both nodes can be removed, which node should be removed first? And if we answer 3 questions, the transforming framework has been done. So we try to answer the questions. And the first question, which node can be removed? We provide the proposition. Suppose that the circuit is with G epsilon XOR matrix, and the in degree and out degree of the node U means the proposition. So the node U can be removed. And for the second question, how to remove one node, we also provide a proposition. Suppose given circuit with 2 input XOR gates, so it can reduce the circuit by removing the nodes with out degree n. And see the example, the node U has out degree 2, and if the condition is right, we can remove U and adding 2 3 input XOR gates, and the area of the new circuit is lower. And the third question, which node should be removed first? The proposition can answer our question. Suppose the upper bound is n. For example, if the out degree of U is m, the out degree of node V is n. If m is greater than n, we can remove V first. Remove the node V will reduce more cost than the node U. And then we answer 3 questions. So we propose algorithms using 3 inputs XOR gates. And then is an example using 4 inputs XOR gates. If the out degree is 1, we use the first figure, and the out degree 2, we use the second figure. And if the out degree is greater than 2, we can use the same method to do it. And this is the algorithm using 4 input XOR gates, and it has 4 steps. First, we receive the implementation of the linear layer with 2 input gates. And then we use the graph extending algorithm to generate many equivalent circuits with 2 input gates. And then we use 3 input XOR gates to optimize the circuits. After that, we also need to use the graph extending algorithm to generate many equivalent circuits with 3 input XOR gates. And finally, we use the transforming framework using 4 input XOR gates and generate many circuits with lower area of the circuit. So we can choose anyone as the best friend, best results. And finally, we can show the application. We apply our method to many linear layers of the matrix, such as the AES, the joystick, the two-fish, et al. For example, we see the AES. If we only use 2 input XOR gates, like the XZ, LBZ, the area is greater than 300. And if we use multi-input XOR gates, like the XZ, LBZ plus EJT3, the area is reduced to 243 areas. So that's all. Thanks for your attention.
Thank you. Do we have question in Beijing?
Yeah, there's a question in Beijing.
I have a question. I know that the linear layers benefit from the multi-input gates, but for the S-box, I want to know if you try to do same work.
Yeah, you say S-box circuits.
Yeah.
We do some work in the S-box circuits. For example, the Boyer et al. Provides the circuit in 2020. Its circuits has divided into 3 parts. The first part and the third part is the linear layer, and the second part is the nonlinear layer. We can use our framework to its 2 linear layers using 3 input aggregates or 4 input aggregates, and we can get a little improvement using the multi-input aggregates. But for other types of the gates, like the AND gates or the OR gates, we leave it as a future work. We hope to generate a general framework with more types of the gates in hardware. Thank you.
Thank you. Thank you.
Any other question?
Yeah, there is a question from Beijing. Hello, Mr. Liu. I just want to know, you know, the latency is a very important factor we need to consider when we designing a circuit. I just want to know whether your algorithm can reduce the depth of a circuit.
Oh, you mean the depth of the circuit?
Yeah.
As you know, the latency is also important in hardware, and the depth is relevant to the latency. So I think our can find a better latency of fiber circuits with lower latency. Maybe we can see the slide. Yeah, in the first we have the we receive single graphs, and then we use our graph extending algorithm to generate many equivalent circuits. And after our optimization method, we generate many better circuits with lower area. And if we focus on the latency or the depth of the circuits, we can also choose one from the many equivalent circuits. And maybe the depth is reduced. I think the method can help you.
Okay, thank you. Thank you for your
Thank you
answer.
so much.
Any other question? Okay, I have one question. Did you try to look at your results coming from your tool when you compare them with the hardware synthesizers? So if you put the matrix, give it as input to one synthesizer, did you try to see what gate equivalent it will give in the end? Like if you try different optimization in the end, did you try like hard, really important optimization with hardware tools?
Sorry, I do not quickly get your question, but you mean the multi-inputs greater than 4 and or other?
So when you do you really try to do a lot of optimization with your synthesizer using like different gates with a larger number of XOR inputs?
We have not do this work. We in previous work we focus on the linear layer, so it only requires the XOR gates. And for other types of XORs, but the other types of the gates may be more complex, and we have not idea to do this.
No, sorry. My point is just that if you use a synthesizer, they might be able to optimize your circuit as well. Even though it's just XORs, it might be able to potentially provide improvements.
I think it's our method can only use in some libraries, not all the libraries, because in some libraries the 3 input aggregates requires more area than 2 input aggregates.
Okay, thank you.
Yeah, thank you. Thank you.
All right, if no more question, then let's thank the speaker and all the speakers of this session.